mass. So this is again one kind of you can say the analysis trick which we'll always follow. That is the modeling. We'll simplify the model. I'll talk about this modeling a little bit later. But so this is a model of simple pendulum, which is a rigid point mass. We'll consider this to be a point mass. That means there is no extension. The moment of inertia about the center of mass is actually negligibly small compared to its mass itself. So this is a point mass, and this is the string, which is again, this is an assumption. This is massless and inextensible string. So the string has no mass, which is of course not the real situation. But compared to the mass of this point mass, the string mass is negligible, and this is inextensible. Again, you see that no string is actually perfectly inextensible. It will deform, but this deformation is so small that we neglect for the for the sake of the analysis. So this is actually the mathematical pendulum, and it is at rest. So this is its equilibrium position. It is at rest. Okay. You'll know later on that there is another equilibrium position. Of course, this will not generate vibration, but this is the equilibrium position around which the body body can vibrate. That means it can have to and fro motion around this equilibrium position. Now let us see what happens then when we disturb it. That means we pull it this side and leave it. Okay. So this is the posture. I pull it at an angle theta naught, and then I disturb it. So you see that there will be a restoring force. Which force is the restoring force now? What is the restoring force field?
Gravitational force.
Gravitational force is now restoring force field. If you draw a free body diagram of this particle, then you will see that the gravitational force mg will act here, and the string tension will be there. And this component, so this will have two components, mg. So this force, instead of that force, you will have two components there. For any angle theta, this will be mg cosine theta, and this will be mg sine theta. Now you see that this mg cosine theta, because this string is inextensible, so tension is acting like a restraining force or the constraint force. Now the constraint force is a force which will be adjusted automatically within itself, so that the particular constraint is satisfied. So this is a motion. This is an example of a constraint motion. What is the constraint? The constraint is that the length of the rope is actually constant. So therefore, it cannot move. This particle cannot move in the along the radial direction. So it can only move along the circumferential direction if you draw a circle with the point O as a center and L as a radius. So the point is capable of moving along the circle, but not radially, because this string is there. So the string will oppose its radial motion. So it will not allow it to go out of the circle. So this is a constraint force, or the restricting force. So this constraint force is the string tension. This is adjusted. So what it becomes, that T will be equal to mg cosine theta. Of course, when the body moves at a different angle of theta, the string tension will be different. Okay, but so it is going to be adjusted. The string tension will be different at different point. This is not important thing, the string tension. But what is important is that this component, okay, mg sine theta. So mg sine theta is our restoring force. So mg sine theta, mg sine theta is our restoring force. And if you allow me to take a coordinate system at this particular point, let us say at the extreme end, so therefore mg sine theta naught is the restoring force, and this force is acting along this direction. Okay, so it's acting along this particular direction. And in this direction, so now this is the total force acting along the circumferential direction, and along the circumferential direction, this is equated to the to the inertial force also along the same direction. So what will be the inertial force here?
Mn.
M A, right? A along the radial direction. So this will be, if I measure theta from this side, so therefore I take negative sign just to indicate that the force is acting in the direction opposite to the angle. That is, I am measuring the angle from here, so therefore this is positive theta. So this is acting along this direction. A more appropriate notation will be used if you use the vectors. But for the time being, let us consider only very simple scalar hand waving kind of argument. So minus mg sine theta is the restoring force, and what will be the acceleration inertia force? Mass times acceleration. Okay, and acceleration in the radial and the tangential direction. And what is this value of a theta dot? A theta, that is the acceleration along the tangential direction. What is this value?
L theta double dot.
Right, L theta double dot. Okay, L theta double dot. So this is the acceleration at this particular point. So if there is an acceleration along in this direction, so acceleration here theta double dot will be equal to minus g by L sine theta. So here you see that at this point when you pull it, then there will be acceleration. Okay, so this, because of this acceleration, its velocity is going to increase. So therefore, because of this acceleration in this direction, now we see the acceleration is theta double dot is negative. That means theta dot will be in the particular direction, that is toward, in the clockwise direction here. So the body will move in such a way that the value of theta decreases. So this is what the restoring force will do. That is, the body will attain the velocity towards the equilibrium position. Okay. So that is it understood? It's a very simple thing, but one should know that what are the primary components of a vibrating system. That will help us in modeling. Okay. So, is it understood?
Yes, sir.
Yes, sir.
Good.
Yes, sir.
Now, what we see here is that at this point, okay, at this point it has an acceleration. So therefore, its velocity will increase from 0. So I lift it from rest, so therefore velocity was 0. Now because it has acceleration in this direction, so therefore the velocity increases, okay, in this particular direction. And it increases and it becomes maximum here. Why maximum there? Because maximum velocity is there. You can see directly from our equation, that is theta double dot equal to minus g by L sine theta. You can integrate this. How to integrate? How do we integrate?
Integrate with time.
By integrate.
Sir, considering theta to very small, sir, sine theta becomes theta.
No, I did not consider theta to be very small. At this stage, I do not, because
Theta dot equals to g by L cos theta plus constant. No. Considering theta is very small,
theta I don't consider very small. Theta can be as large as possible.
Sir, theta double dot can be written as d2 theta by dt2,
Yes.
and then we take that dt2 from that on that side, g by L sine theta side, and we integrate the equation.
You try, take 5 minutes time and try whether you can get that. 12 degree students? Any student?
Sir, vibration is for small oscillation, na?
No, not necessarily. Only for small oscillation we'll have, am I audible?
Yes, sir.
Okay, for small oscillation we'll have some properties of oscillation which we'll call actually linear vibration, but vibratory system can be non-linear also. So in this particular system actually it's a non-linear oscillation part. Vibratory system is actually a non-linear vibratory system. If the angle is small, theta is very small, then we can linearize it. Okay, so it becomes then linear equation of motion. But it's definitely possible to have large amplitude oscillation. There is no harm in it. It's not true that the vibration amplitude has to be small always.
Sir,
Small
we can give my colleague.
actually save our some effort because the analysis becomes simple. But most of the vibratory system, I'll tell you where well, nonlinear vibration is actually you can say that nonlinear vibration is actually more often than the linear vibratory system. Linear vibration is a small domain of nonlinear of total vibratory system. Okay. Okay, coming back to our integration. So how do we do that?
Sir, we can, so integrating the g by L sine theta in dt. So instead of dt, we can give d theta by omega.
No.
So I just considered that dt in the g by L sine theta dt. Instead of dt, I just considered d theta by omega. D theta by theta dot.
Okay, let me try what you are saying. D. So I'll have d2 theta dt square.
So that is d omega by dt.
Okay,
Okay.
this sine theta.
Sine
Okay,
theta.
d omega by dt, fine, equal to minus d by L.
Sine theta.
Theta is equal to omega t.
Huh?
No.
Theta equal to?
Theta is equal to omega t.
Theta is not equal to omega t. Please understand, when you say something, be careful. Theta, d theta, this is equal to omega. It does not mean that theta equal to omega t. This happens when omega is constant, but angular velocity may not be constant. And in fact, if you hear it is not constant. Okay. So be careful in this kind of operations. Don't assume anything arbitrarily. Theta cannot be equal to omega t. And if you take omega t here, then you cannot even integrate because these two omega and t, these two are again coupled here, then omega and t both are appearing there. So then the integration becomes impossible.
Sir, we can use energy conservation.
That is another aspect, but that is what I wanted from you. But let us say when we have started this particular integration that we completed, now what I have d2 theta dt square, this is equal to minus d by L sine theta. Okay, so this is why now I'll write down d2 theta dt square, d2 theta dt square, this is equal to, okay, d theta dt and d2 theta dt and d2 theta so what is this one is d theta dot dt. Let me write down this way, and this becomes equal to d theta dot d theta times d theta dt. Is this clear? Right? And this becomes equal to theta dot. This is d theta dt is theta dot, and this becomes have you followed? D
Yes, sir.
theta dt square equal to d theta dot dt. Just a notation. Theta dot is d theta dt. Just a notation. So this becomes d theta dt, I then write down theta dot as a function of theta, which is of course a function of time. So theta dot d theta and d theta dt, and theta d theta dt is nothing by definition is theta dot. So therefore this becomes d theta dot d theta. Okay. So if you write it down here, then this becomes theta dot d theta dot d theta equal to minus g by L sine theta. Okay, set. Then this becomes, if you take d theta other side, so therefore you can write down this as d theta. This becomes d of theta dot square by 2, and that is equal to minus g by L sine theta d theta. You may not see so well, so let me write it down on top. This board is small, so therefore I have to erase and rewrite many things often. So please bear with this. So this is what we have, d of theta dot square by 2. This is equal to minus g by L sine theta d theta. Now this is actually integrable because two variables are now separated. You integrate from, let us say, theta naught. It was extreme position was theta naught, and it is coming to a position, let us say, at theta. So it was initially at theta naught, and now this is at theta. So it has come from theta naught to theta. So theta naught to theta, and the corresponding velocity here at theta naught, its velocity theta dot was 0, and this maybe I'll consider this as theta dot. Okay, so theta dot as at particular angle theta. This I name this velocity as theta dot. Now if you integrate, then this becomes theta dot square by 2 equal to g by L minus cosine theta. So theta naught minus cosine theta naught minus cosine theta, right? Yes?
Sir, there won't be a minus, I guess.
There will be?
Like integral minus sine theta d theta is cos theta.
That's what. So,
Be cos theta minus.
so it was from theta naught to theta.
Sir, he is saying that cos theta naught will become on other side.
That's what you mean, right?
Yes.
Yes,
Sir.
sir.
Yeah. Okay, so this is what we have. Now you see one thing that the velocity, because of the nature of this function cosine, the velocity will increase as theta becomes small and small, right? And when theta is equal to, so this becomes equal to, so when theta, so theta dot maximum will be at, this is at theta equal to 0 degree. So when theta becomes 0, the theta dot will be maximum. So it will have the maximum velocity at this particular point when theta is equal to 0. And what will be this value? This value will be equal to g by L and cosine. So this will be 1 minus right? Now this equation and this, from that you can find out this will be equal to 1 minus cosine theta naught equal to 2 sine theta naught. So therefore this is 2 under root g by L, and this becomes equal to sine, kind of, right? So this is what we have. The maximum value of theta dot will be like this. Fine. I just put 1 minus cosine theta dot theta naught equal to 2 sine squared theta naught by 2, and then I took the square root of it. So 2 under root GL sine theta naught by 2. For a small angle, actually theta naught becomes, if theta naught is small, then this becomes under root G by L theta naught. Is this clear?
Yes, sir.
Okay. Now you see the maximum value of the velocity is when the particle passes through its equilibrium point. So at theta equal to 0. Okay. Now, what is going to happen that at this point there is no circumferential acceleration because the total force is downward. Entire force is downward, so there is no component along the tangential direction. So there is no force along the circumferential direction, but it has a velocity. Now here comes the inertia part. Now what will happen? Because of the inertia, this body will not come to rest at this point. It will continue to move because Newton's law says so. It will continue to move with the velocity v at this particular instant. Okay, because there is no force in the tangential direction. So in the tangential direction, it will continue to move. As soon as it continues to move, what is going to happen? Again, the restoring force will come into play. So it will cross this one and it will come at certain point. And when it comes to this particular point, then its restoring force will again act and it will try to bring it just as it was doing earlier. So therefore, the motion actually, it becomes, at least it does not stop here, it crosses there. But then what will happen? When its velocity will be 0? When the velocity is 0? When velocity becomes 0, because if theta is equal to plus minus theta naught, you see that theta dot equal to 0. Okay. So when theta becomes equal to minus theta naught, that means in this direction, minus theta naught, again its velocity becomes 0. So this now all becomes the same thing as the first starting point, but in the opposite direction. Okay. Now the completely it becomes kind of a symmetric with respect to the vertical axis. So what is going to happen? Then again, because now the posture, the velocity, everything is same, so therefore the motion is same and it will continue moving like it did in the first instant. So this way we can see that this restoring force is needed because without restoring force the body cannot come back. But inertia force is also needed because without inertia the body cannot cross the equilibrium point and it will not sustain the oscillation. So inertia effect and the stiffness, somebody said the spring constant, spring stiffness and so on. There is no spring here, but what by stiffness, what possibly we very casually say, we mean that this is a restoring force. So there has to be restoring force and there has to be inertia effect. So with these two things, the body can continue oscillating. So there will be to and fro motion. Is this clear?
Yes, sir.
Yes, sir.
Yes, sir.
Yes, sir.
So
Yes,
the
sir.
whole,
Sir.
yes.
Sir, I have a doubt, sir. Sir,
Yes.
as you said that spring constant, that stiffness is not necessary, but if we check that in practically, but every object is not ideally rigid. So every object has some stiffness. So stiffness is also necessary.
Yes, every object has stiffness, but when you are considering, say, this is again, for example, let us take this. This is a vibratory system. Do you agree?
Yes.
The motion which this bob executes, we call it vibratory motion. Is correct?
Yes.
Now let us, with respect to this system, let us see what is meant by stiffness here. So this is one. Now you say, and definitely it is very much realistic, that everybody has kind of stiffness. That means if you apply force to anybody, any longitudinal force, it will elongate, right? That's the Hooke's law says that, isn't it?
Yes, sir.
Everything has elastic property. Fine. So let's say this. There are two bodies here, in and this is the mass and this is the length. This is a string. So the string has elastic property. Okay. So if you extend it, so what will happen that if you apply a force to it, so it will elongate. So it will have a stiffness, right? So you can model this as kind of a string, isn't it? Because it
Yes,
will have
sir.
stiffness, so it will elongate by amount delta. So therefore, EA by L will be spring stiffness, the constant,
Yes.
right? Okay, fine. So this is the spring constant. Now what will happen? So what becomes of this of our model? This model becomes like a spring. Instead of a string, of course, this is very large quantity it has, because Young's modulus is very large of this, because this is inextensible. I said that, but actually I considered K to be here infinity. I considered earlier, but now for this time being, I will not consider K to be infinity. K has a finite value, let's say. Now what will happen to this one? Now as it moves, if you disturb from equilibrium, so now you can disturb in two ways. Okay, either you can pull it
Back
one side,
and forth. To and fro motion.
and you can of course stretch it here, right, downward direction, and leave it, isn't it?
Yes.
Okay. So what will happen that now what we are saying that suppose this is the free length of the spring and this is the circle. So what will happen that this is
But
here.
this will be
Right?
of second
It's not on the circle because it has stretched. The spring has a spring constant, so therefore it has stretched. Am I correct or any confusion?
correct, sir.
Okay, sir.
Okay. So it will stretch. Now it is capable of. So what this spring is doing, this is the equilibrium position, and now in the radial direction it has stretched. Also in the circumferential direction it has moved. Right. So what this spring is doing? Yes, I cannot hear. I mean, voice is breaking. Yeah, tell me again. Yeah. Who? Hello.
Yes, sir, continue.
Am I audible?
Yes, sir, you are.
Yes. Now tell me. This is the most frustrating part. I cannot see you. You are trying to say something, but yeah. Bolo.
Sir,
please
continue, sir.
Okay.
I don't know who are.
Okay. So the string, this will be stretched, right? So what this string is doing is actually it is trying to restore the towards this equilibrium position. So it has kind of two ways of departing from this equilibrium. One is that in the tangential direction and another in the radial direction. So this spring is actually pulling it towards the radial direction. Okay. And in our case, we took this delta, string to be inextensible, so therefore the stiffness is infinite, and there was no deformation along the radial direction. Of course, this is very small deformation will always be there, but this will make, of course, the system more complicated. Later on, we'll see that this is also a vibratory system, but this vibratory system has some other characteristics. This is a vibratory system which is more complicated in the sense that it has more degrees of freedom. We'll take up this term, this degrees of freedom. So it will have more degrees of freedom than the simple pendulum. Pendulum had only 1 degree of freedom because it was capable of moving only along the circumferential direction, but now this is capable of moving also in the radial direction. So it has another degree of freedom. Okay, so this thing makes the thing more complicated. But what I say that this spring is not needed. Okay, the spring was not necessary. I could have taken the spring constants to be infinity. Still, the body executes vibration. Another thing which is actually is unrealistically model, this is the mass over there, right? The mass I took as a rigid mass. Of course, as you pointed out that there is no mass which is rigid, everything is deformable. So there may be a kind of deformable, so this body may be deformable body, but if you consider whatever be the internal deformation, etc., if you consider the center of mass of this system, so this can be taken to be a point mass, okay, center of mass, where the total mass is actually assumed to be concentrated. So if instead of considering the entire body, which may be deformable or such, if you consider the center of mass and consider the motion of the center of mass, so the center of mass is actually executing a vibratory motion, okay, oscillatory motion. So it is not necessary that all the bodies here has to be deformable. Is this understood? Deformation is there, but for vibration, deformation may not be required, as you have seen that there is no deformation anywhere. But there is vibration because there exists a restoring force field. So the gravitational field is actually acting like a restoring force field. So whenever the body is trying to move, so this pendulum is trying to move, then the gravitation is actually, the weight is actually bringing it towards the equilibrium posture or equilibrium position. So there is no spring here, but effectively gravity is acting like a spring. In the sense, I mean, if you, in the very loose sense of the term, if you consider spring is the only object which gives a restoring force. So then gravity is acting like a spring. But otherwise, there is no need of any physical spring. Only we require a restoring force. Is this clear?
Yes, sir.
Yes, sir.
Yes, sir.
Okay.
Yes, sir. Very clear.
Right. So you now see the equation of motion here. You see, equation of motion I have already written, theta double dot plus g by L sine theta equal to 0. Okay, so this is the equation of motion which it was very simple to write down here, because just using, because there's a single particle and we had only a single restoring force. So it was not very difficult. But later on, in the later coming classes, we'll learn how to write down the equations of motion and how to systematically generate the equation of motion. Newton's law, using Newton's law is one technique, of course, but there are other techniques which are more algorithmic, okay, more routine, which I suggest that you should master those techniques. Okay. Now, anyway, so this is our equation of motion. One thing you see here, that there is certain symmetry which you can observe. If you change theta to minus theta, okay, theta to minus theta, okay. And of course, when I write down the differential equation, I of course should tell the boundary condition at theta equal to 0, let us say theta naught, and theta dot and theta equal to 0, this is equal to theta, or maybe I'll solve this. Okay. So these are the initial conditions. So what we'll solve in these vibration classes are just this kind of initial value problems. Of course, there will be, the right hand side will not be always 0, there will be other terms there, but we will have always certain initial conditions. So this is kind of what we, in mathematically, we call this initial value problem. Okay. So initial value problem, the differential equation is given and the initial conditions are given. So with this initial value problem, what you see here is that if you change theta to minus theta, necessarily theta naught has to be changed to minus theta naught, and omega naught has to be changed to minus omega naught. So in that case, you will see that the equations of motion and the initial conditions, they do not change, right? If you put theta equal to minus theta there, then sine theta is minus theta is minus sine theta. So the equation of motion again remains the same. Have you understood what I want to say? if you substitute theta by minus theta everywhere, then you'll see the equation of motion does not change, because in the equation of motion it becomes minus theta double dot plus g by L sine minus theta equal to 0, and that again becomes theta double dot plus g by L sine theta equal to 0. The equation of motion remains the same. Okay. Also, theta, here also theta substitute by minus theta at time t equal to 0, and this becomes minus theta naught. So therefore again the equation remains, this initial conditions also remain same.